In this video, I'm going over the start of compound events. So when finding probability of compound, more than one event. So events could be independent, where they are not affected by each other. So one does not depend on the other outcome, or they are dependent, where one will depend on the other, which will affect the probability of the second outcome. So like here, for example, just being able to identify here. So like if I were to flip a coin and roll a six-sided die, are these events independent or dependent? Well, they're independent, right? Because here, does it matter? Like if I flip a coin and let's say I get tails, does that affect the outcome of what I roll on the die? No, they are independent of each other. So a bag contains 10 beads, right? So 2 beads are selected at random, but without replacement. So let's just say that means the probability of the first event occurring, like let's say it's by color, right? Like 5 red, 5 blue. The probability of the first event is out of 10. But because you did not replace that first bead here that you chose without replacement, notice how the second event, the probability of that occurring now is now out of 9. So that's what makes this situation dependent, because now you changed the event, the probability of the second event occurring. So here, you draw from a standard deck of cards with replacement. That would be independent, right? Because you take a card, you put it back with replacement. You spin a spinner with 6 sections 5 times. That is also independent, right? Every time you spin a spinner and it's got 6 sections, does that mean that you're going to now change the outcome or the probability of every time you spin it? No. Every time you spin the spinner, it is independent. So again, just to reinforce this idea of independent, but with our given situation. A coin is flipped, and a cube is rolled. We're going to let A represent that the coin lands on heads. And then we're going to let B represent that the cube lands on the number 4. So A landing on heads, B landing on 4. So like here, for example, what's the probability of event A? Well, that's just 1/2, right? You land on heads, 1/2. So now, again, keep in mind, right? These two events are independent of each other. We talked about that just about a minute or so ago. So now just to show you, this says, what is the probability of A occurring given B? So given that the die landed on the number 4, what is the probability of the coin landing on heads? Well, still 1/2, right? Does it matter does it change the outcome of A given that you landed on the number 4? No. So again, that's why they're independent. So again here, what is the probability of A but given not B? So let's say you don't land on a 4. What is the probability, given that you don't land on a 4, what is the probability that A occurs? Well, that's still 1/2. So here, what do you think for these 3? So the probability of B landing on a 4 is 1 out of 6, right? That's our standard 6-sided die. So then what's the probability of landing on the 4, given that you landed on heads? Well, it's still 1 out of 6, right? Doesn't change. What is the probability that you will land on a 4, given that you don't land on heads, that you land on tails? It is still 1 out of 6. Because again, even with the given, with independent events, notice that first event will still be that probability. It doesn't change. So here, now let's get into some probability. 2 M&Ms are randomly selected. What is the probability that the first selected is green and then with replacement? So what does that mean? independent, right? You put it back, then selecting blue. So now here, what is the probability of selecting green? Well, the green is 5 out of, well, how many M&Ms are in the back? 32. So then here now, what is the probability then with replacement? So it's still out of our 32, right? That you get a blue. So there are 9 out of the 32. Now, because this is a compound situation, not like an OR situation where we're going to combine them, we are going to multiply them now. So here, multiply your fractions, and you should get 45 out of 1,024. So here, we'll do the next, I'll go over the next one. So 3 M&Ms are randomly selected without replacement. So now notice this is a dependent event. So now the second and third event, right, because we're choosing 3 M&Ms, depend on the first. So keep that in mind. So what is the probability that the first 2 selected are red? Well, here we go. So what is the probability of getting red right now? 4 out of 32, right? That is just the probability of getting the first red, right? Because there's been no other picks. However, now what is the probability, because it's without replacement, of then getting another red? 3 out of 31. Because think about it, right? Let's say I chose a red. So now the probability is 3 out of 31. Then what is the probability that the third one is yellow? So out of 30, how many yellow are there? 3. So again, notice how dependent those amounts are changing. So now go ahead and pause to multiply and simplify. And you end up with 3 out of 2,480. So that is the probability in this situation that the first 2 selected are red and the third one specifically is yellow without replacement. You have a 3 out of 2,480 chance of that situation occurring. That's what that probability means. So here, I'll go over also these with the cards. And if you're unfamiliar, here is the image of our deck of cards. So there are 52 cards total in the deck. There are 13 here, 13 clubs, 13 spades, 13 hearts, 13 diamonds, right? 13 times 4, 52. Then notice here there are 4. So 4 kings, 4 queens, 4 jacks, so on and so forth. All right, so keep that in mind. What is the probability of choosing 2 face cards? So that's your jack, queen, king in a row with replacement. So that means independent. So here we go. Out of the 52, how many face cards are there? There are 12 out of the 52. Oops, sorry. So there are 12 out of the 52. And then what's the probability of choosing another face card? But again, with replacement. So again, 12 out of 52 and multiply and simplify. And so now let's go here to this next one, but I'm going to change it. So let's do the same type of problem. So what's the probability of choosing 2 queens, but putting it aside? So what's the probability of getting 2 queens, but putting the pick aside? So again, now how many queens are there? There are 4 queens here, right? So 4 out of the 52. But again, let's say you choose it, right? You put it aside. So now the probability is 3 out of 51. Because again, keep in mind, you chose a queen. That's what we're looking for, right? The probability of choosing a queen. So now you multiply. But again, keep in mind, because you put it aside, this is dependent. So that total changes from 52 to 51. So then here, just to kind of show you how to identify your independent dependent events, but in a table format. So here, for example, are the events have been to Mexico and have been to Canada dependent or independent? So again, remember, independent events are, even though there is a given, the first probability is still that answer. There's no effect, right? So there's no effect to it. So here, we're going to test using that given situation. So are the events, we're going to test the probability of been to Mexico given they've been to Canada and see if that's the same as the probability of going to Mexico then, right? That's what we're saying, if they're independent of each other. So here we go. What is the probability that someone has been to Mexico, but given they've been to Canada? Well, how many people have been to Canada? 11. So out of those, how many have also been to Mexico? That's our and, right? So 6 out of the 11. And what is the probability that someone's been to Mexico? 6, but out of 9. They are not equal, so they are dependent. So that's again how you test to see, right, with that situation. So again, even in words, the probability that someone plays sports is 65%. So we're saying that this value, the probability overall is 65%. The probability that a person is between, or that a person is between the ages of 12 and 18 is 40%. So 12 to 18 is 40%. But then the probability that the person plays sports and between the ages of 12 and 18 is 25%. So notice this combo, the and, is like our numerator. So here, the 26%, we are going to then, out of the total number of people who are the ages, so 40%, and we're going to go, all right, is that equal to the probability that someone plays sports? And so here, if I were to also convert, right, so 0.26 divided by 0.4, is that equal to 0.65? Yes. So notice how, again, that and, that combination of the two events is in that numerator. So let's say, well, Miss Reiner, it's got to work both ways, right? So again, our and, the 26%, 0.26, let's say now the other probability of playing sports, 0.65. We're saying that that should be the same as just finding the probability that someone is the ages of 12 and 18. So again, are they equal to each other? Yes. So as long as you make sure, right, that that combination of the two events together, your and, is in the numerator, just like when we had our table.